In this video, I want to introduce inverse functions. So we've actually been looking at inverse operations and inverse functions for years without calling them inverse functions. So for example, if we're talking about inverse operations, we could have plus and minus, or times and divide. So we use the word inverse, it means opposite, or it means that one of them is undoing the other one. Some of the inverse functions we've looked at most recently are e to the power of x and log to the base e of x. So we know that they are opposites of each other, or inverses. One of the first types of inverse functions that you would have been introduced to are trig inverse functions. So if you had sine x, and we could have sine inverse of x, which is one of the first ones you use, and that's the button on your calculator. So I want to have a look at some examples of inverse functions, and later we'll look at how we found them. But our first example, if our original function was y equals x plus 2, then our inverse would be the opposite, which would be x minus 2. A second example might be if we had the function y equals 3x, then its inverse, the opposite, would be y equals x divided by 3 instead of multiplied. And the third one we've already talked about a little bit, but we're going to have a look at what it looks like graphically. So if we've got y equals e to the power of x, then its inverse would be log to the base e of x. So let's have a look at what they look like graphically. So our first function was y equals x plus 2, which is this red line here. Our second one is going to be the line y equals x minus 2, so that's its inverse. Our second example, we had the line y equals 3x, which is our red one. And if we wrote x divided by 3, this has approximated it, but it would look like this. In our third example, we had the function y equals e to the power of x, and then we have our log to the base e of x as our inverse function. Now what I want you to notice about all of these is they have a special type of symmetry. So if we have a look back at our first one, I'm going to introduce this line just y equals x. And you can see that that's a reflection over that line. It's not as obvious with straight lines, but once we get to our third example, hopefully you'll be able to notice it a little bit more. So our second example, we'll introduce that same line, y equals x, and you can see that if we were to take these functions and fold them up along that line, y equals x, that does have that symmetry across that line. And it probably gets a little bit more obvious when we have a look at curves, and you can really see that symmetry across that straight line again. So inverse functions all have that symmetry about the line y equals x. So that's the definition of inverse functions geometrically. Algebraically, inverse functions switch the input and the output values. So they switch the x and the y. So the numbers that were our x values become our y values and vice versa. We also need to look at the notation used for inverse functions. So if our original function is f of x, then its inverse is denoted like this. That's f inverse of x, or f of x inverse. Now we have used that notation before. Like I said, if we've got sine x, then we have sine inverse of x. Keep in mind that that is not a power or an index, so it doesn't mean 1 over f of x, just like this isn't the same as 1 over sine x. So that's not the same thing. And make sure you're not reading it as f of minus 1. Make sure you're actually reading it as f inverse. So we want to have a look at some of the properties of inverse functions. The first one is if our original function f of x has domain where x is between a and b, and has a range where y is between f of a and f of b, then the inverse function is going to be the opposite. So the domain is going to be what the range used to be, and the range is going to be what the domain used to be, because we're switching the x and y values. And that makes sense when we have a look at functions that we already know. So if we have a look at the function y equals e to the x, we know it looks roughly like this. So we know that its domain is all real x, and its range is y is greater than 0. Now if we have a look at the graph of y equals log to the base e of x, we know that it looks something like this. It's not the neatest graph. So its domain is x is greater than 0, and its range is all real y. So what was the domain has become the range, and what was the range has become the domain. The other property I want to have a look at is that these functions undo each other. So if we take the inverse and then we apply the function to that inverse, we're just going to end up with x, and it works the other way around as well. Let's have a look at some examples of that. So this is one of the functions we were looking at before. If our original function is x plus 2, then its inverse is x minus 2. So we can use either of these because they mean the same thing. But if I do f of f inverse of x, then that's going to be f of, well, the x inverse, this whole bit in the bracket, is my x minus 2. Now, if I want to find f of x minus 2, then everywhere there was an x in the original function, so here, I'm going to replace that with an x minus 2. So I'd have x minus 2 plus 2, which will just give me x. So one last example, and this one I'm going to do it the other way around instead. So if my original function is e to the x, my inverse is ln x. So if I wanted to find the inverse of f of x, then I'm going to have f inverse of f of x was my e to the x. So that means everywhere there was an x here, I'm going to replace it with e to the x. So that means I'd have ln, or I could write it as log to the base e of e to the x, just so this is extra clear. We know that we can bring the x down the front using our log laws, so we'd have log to the base e of e, but log to the base e of e is just 1, so that's just going to give me x. So that's an introduction to inverse function and having a look at some of its properties.